Hi out there and welcome back. Today I'm talking about the binary search that has a really nice iterative and recursive version. It relies on the divide and conquer strategy, and there's a really strong precondition, and that is that the data has to be sorted before we can use binary search. It has a very good runtime of log n in worst and average case. So let's have a look at the algorithm. Well, we get as an input the search value and an input array that is sorted. And then we halve the array step by step and look always in the middle if the actual value is the same as our search value. So because it is sorted, if we are in the middle, we can say all elements on the left side are smaller and all elements on the right side are bigger than our middle element. So it really works out, and that is the need for the precondition. Well, let's have a look at an example first. Well, we have here the initial list 75, 38, 42, 1 and 10. But we need it sorted, so we have to sort it first. But here I want to show you first that if we would do that algorithm on this list, it wouldn't work. Because there, if we are in the middle, 42, then if we compare it to our search value, let's say we search for 1. Then we can't say the 1 is left or on the right side for sure, so we can't divide our array. But if it is sorted like this, then imagine we want to search for the 1 now. Then we go in the middle element and look for the 38. Like this, we search for the 1, and then we compare the 1 with the 38 and see it is smaller. So now we know actually that we have to go on the left side of our array, left of the 38. So okay, now we just have to look in the 1 and in the array of the 1 and 10 if there is our 1 included. So we take these, and again we look in the middle. There is no middle with two numbers, so we have to decide for 1. In this case I decided for 10, so we see the 1 is smaller than 10, so we have to look on the left side of the 10, and there is just a singleton data point or a singleton array, singleton list, and that has to be our 1, or if it is not included in our array, then something else. But in this case, it works out fine. So we found our element and return our index 0. Let's have another look on if we search for something on the right side. Here I have our array again written down, and we search for the 42. So again, we take our element in the middle of the array and compare it to the 42. The 38 is now smaller than the 42, so we have to look in the array on the right side of the 38 if the 42 is included. So we take these. Since I decided earlier on that I take the bigger element if we divide the index by 2, then that I do this consistently also on the right side. So here I also take the right element, the 75. So this is also bigger than 42, so we have to look now on the left side of the 75. So we just have this singleton array with a 42, and this is obviously equal, so we can return our index 3. Alright, now we have to have a look also at a little bit of math, because if we have an array and we want the middle, then it is not that easy, because we have to make a fixed point on our starting point. In this case it is usually the 0, because indexing an array or a list usually is they are indexed by 0. So if we have an array L and R, let's say that are our indices of our array, then it could be, for example, L could be 0 and R could be the length of our array, or the length minus 1. So we have R minus L elements in it, and if we want the middle point, then we simply divide it by 2. But if we have a subarray, let's say the array 5 to 7, then our array, our range of indices is a little bit shifted. And if we do the same then we have 7 minus 5 is 2 divided by 2 is 1, and that is not even in the array. So we have to shift it again a little bit, and we have to shift it by our left limit. So we say, if we have again 5 to 7, then we calculate 7 minus 5 is 2 divided by 2 is 1, plus our left limit, and that is 5 in this case, so we get out at 6. Alright, let's have a look at an example for that. So if we have the indices 0 to 7, then our left is 0 and our right is 7. So we have right minus left divided by 2 is 3.5. And there we can decide whether we want the 3 or the 4 as our middle indice. That is kind of clear, I think. But if we just have a range of indices, let's say 5, 6, 7, and we want it in relation to the 0, then we also have to add the left limit. Here, left is 5 and right is 7. So, right minus left divided by 2 in this case is 1. And if we then add again the 5, then we are at 6. The indice 6 is actually our middle indice. Alright, let's implement that in Python. For that, I create a new file. Let's call it binarysearch.py. And there I create a class binary search. And in that class I want to show at first the iterative approach and thereafter the recursive approach. Okay, let's say we define a method search iterative, and this gets self as usual in Python classes, and it gets also our data and our search value. Alright, let's do some documentation for this. We say data has to be an array that is sorted ascending in this case and has numeric values. And we say search value is the value to search for in data. And we say it returns the index of search value in the data array, or none if it was not found. Alright, so at first we need also some little helpers for our approach, and that is we also always need the left and the right limit we are currently searching on. And so we need, let's say, left, and we can start the left with 0. And we take the right, and we say right is our length of the data array, so the last indice minus 1. And then we want our index. We don't need our index right now. Alright, so we say while, and for now I just say true and say exit condition here, because we will fill that in later. Alright, so the first step now is to find the index we are comparing with our search value. So we say index equals, and now we can fill in our formula that we had earlier, where we tried to find the middle index in the array. and that was left plus right minus left divided by 2. So here we also have to set the brackets. And there's one more important thing. Since we divide here numbers, we also should include a math package called Python package called math, which gives us the function ceil, which rounds to the next higher integer number. Okay, so here math.ceil, and we want this approach. And this was because in our example we had the 3.5 and we had to decide for one of those numbers. I decide for the bigger number in that case. Alright, so the first thing we need to do is we have to check if our data point at position index is the same as our search value. If so, we can return this index and we are done. So here we can say search value found, and we say if data index, the index, that's the data point at our index, equals to our search value. Then we can say return index. Alright, so now we have two more cases. One is that our value, our search value, is smaller than the data point at position index, and one that it is bigger. Alright, in the first case we say it is smaller, so search value is smaller than the data point at index. So here we say look on the left side, and there we can now make a little trick. Because we have our index, we just need to move the right limit. So now we can say right is equal to our index minus 1. Since we already compared this with a data point at index, at position index, we don't need to have a look at it again. Alright, and now we have to look on the right side and on the right side. And that is in our else case. And we can say we move our left now, and that is index plus 1. Alright, now we are almost done. There's one thing left. If we didn't find any point, or if this didn't find the search value in our data array, we return our none value. Alright. So what is going on now with our while condition, with our exit condition? There we can say if the left side is bigger than our right side, then we want to exit. So we say if left is smaller or equal to our right, then we want to stay there. Because if we went over with one side, then we didn't find any value equal to our search value. Alright, so let's test this now. For this I say if name equals to main. So we enter our main class in our program. Then we say bin search is equal to our binary search class, so we instantiate our binary search class, and then we need a data array. Data is equal to, and yet now we can take some random numbers here. I like to use something like this, maybe, so that should be fine. Alright, and now we can call our bin search on our data, and let's say we want the 1 here in this case, So let's print the index. That should be 0. And if we run this program now, then we still get object is not callable. I need to use the method here. Sorry, I overlooked that. We called it search iterative. Alright, let's run it. And we get the index 0, that is right. Let's do it also for all others. Or better, we can use a loop here. So let's say here for I in data, we search for I. And let's copy that quick, and because I also want to look what happens if we are outside of our on the left side of our array, if we are outside on the right side of our array for searching a value, and if there's something in the middle that we may look for. Alright, so let's run this again, and there we go. We have all our values from 0 to 5, and none, none, and none for -1, 10, and 3. Alright, so far so good. Let's implement our recursive version. For this, I create a method called search recursive, and it gets again self, our data, and our search value. And here we for now say just continue as a placeholder. Or we say return as a placeholder. Because there we have to call our recursive helper method, and this will have a few parameters more. So we say def search rec as a helper, and I make it private. And then I say self data search value, and in each step it needs the index, it needs left, and it needs right. And actually it doesn't even need the index, we can compute it in our function. Alright, so at first we can say we return or we exit from the recursion if we found an element. So if therefore we have to create our index variable now, and that is again left plus right minus left divided by 2. And there we do again a math.ceil to round up to the next bigger integer, and then we say if search value equals to our data point at position index, then we return index. If not, else if. Here we look again for the left and the right side. Here we can say value found, and here we can say look left. So here we say search value is smaller than data at position index, and there we call again our self search rec function, and we give it data search value, we give it left, and we give it index -1. In this case again because we search 1 to the left of the index. And otherwise we say we do the same here, just with index plus 1 in here now. Alright, that looks good so far. Here we comment it too and say look right. And here we need actually left to be index plus 1 and we keep right as it is. And then we need also one more thing, and that is the abort condition if our left is bigger than the right. So if left bigger than right, we say return none. Alright, and that is basically it. Now we just have to return up here our self dot search rec with our data, our search value, left is 0 and right is data, and we want plain data -1 here. Alright, so that should be it. Let's see if that works. So we can do here the same. We just have to change this to search recursive and see if it works. Let's start it. And we get an error here. It says binary search object has no attribute named _binary search. And we probably have here a spelling mistake. Alright, let's try it again. And this didn't work now. So where is the mistake? We have to return those here, because otherwise we don't forward it to the higher stages when we keep going from our stack. Well, that works. As you can see here again, we have our good output and we have our outputs for the respective values outside of the data array. Well, ladies and gentlemen, that was it for this video. If you liked it, give it a thumbs up and subscribe to the channel. Well, you can leave the comments down under the video. I always love to read your comments, and maybe you have some improvements for me or some suggestions, some hints. Well, I'm grateful for everything, and that's it for this video. Have a great day. Bye.